First thing we're talking about is angle measure. Okay, that's all this chapter is about, is determining how we measure angles, and then towards the end it gets some story problems and how we figure out distance if we know angle measurements, and figure out area, sectors if we know angle measurement, that kind of stuff. So if you guys have done anything with like linear velocity and angular velocity in physics, like if I take let's say, take a rock and tie it to the end of a string and I start spinning that around my head. Okay. You just did that? All right, so we can talk about how fast that angle changes, or we can talk about how fast that, if that rock was moving in a straight line, we can figure out how fast that rock is moving, which would be the linear velocity, right? Okay. We can talk about, if I understand how big a wheel is and how fast that wheel is revolving, I can determine how far I will travel just based on the revolution of the wheel. Does that make sense? So those are all things that we can do once we know an angle.
Can you do the last one?
Back up there. See where it says 25 is there? Just go ahead and write that down. Don't get it wrong. Zach got it wrong. Yeah. It's embarrassing. All right. So when we talk about angle measurement set, we have two types of angle measurements, and one of them we've talked about in a geometry course, and it's a positive angle. Okay. But in geometry, when we talk about positive angles, it was always an angle between 0 and 180, right? For the most part. Every once in a while, we start talking about 360 degrees being the number of angles, or the total number of degrees for a circle. But usually, we didn't talk about a 270-degree angle. Okay? Because if we talked about a 270-degree angle for us in geometry, it might have been easier to talk about its 90-degree counterpart. Does that make sense? Or if I talk about a 210-degree angle, it might have been easier to talk about its 170-degree counterpart. Okay. In trig, we usually don't do that. If I want to talk about a 270-degree angle, I talk about the 270-degree angle. If I want to talk about a 245-degree angle, I talk about the 245-degree angle. Okay. So a positive angle is simply an angle that has rotated north. Okay. If we're thinking about putting this thing in the coordinate plane. Okay. Just some terminology here. This here. This ray OA, okay, that is what we call our initial side, okay, and the idea is when we like to kind of think about angles as being kind of dynamic, and we're able to move them and adjust them. So I'm going to show you this with GeoGebra here in a moment. But both our rays start off at the same position, okay, and then I take that blue one and I move it off of the original one, okay. And the blue one stops somewhere in the coordinate plane, and that blue one is referred to as the terminal side. Terminal means end, right? Okay, or to end. So my initial one is the one we start at. The terminal one is the one that ends, and then the span between them, okay, that measurement between them is the angle that we're interested in. Okay. So can I give you a visual of what I'm talking about here? See here. All right, so if I'm looking here, right now, the two rays are on top of one another, right? Okay, so we have an angle of 0 degrees. Okay, when I open it up, okay, this side here was our initial side. Okay, and we would like to keep it as the positive x-axis if we can. And this side here becomes our terminal side. Is that doable? And if I move in that direction, so I started here, and I move north, okay, I move upwards with C, or I move counterclockwise, if I'm thinking about moving in a circular motion, you always get a positive angle, okay? And that positive angle, if I want to talk about a 210-degree angle, we'll talk about the 210-degree angle. Does that make sense? In geometry, maybe it was more convenient to talk about that angle. Okay? But we're going to talk about the green one. And I can keep going, and I can get to 360, right? Okay? But in trigonometry, we can actually go a little bit further than 360, and I can go all the way around again, right? So how far would that be? 720. Olympics start February 8th, right? Zach, you like the Olympics? You ever watch the half pipe stuff? When they do 720s? What's that mean? Yeah, they've done a 360 two times in a row, right? Okay. So we could talk about angles that are bigger than 360. So those are some things that we're going to investigate, okay? And in geometry, we kind of restricted ourselves to 0 to 180. There's no restrictions now, okay? So a positive angle is that movement counterclockwise, okay? Now, what happens if I would have gone from here this direction? Now, don't worry about this angle here anymore. I want it to hide, actually. Go ahead. All right, so I start at B, but now I move that direction. The angle that we're interested in is now this angle between the red and blue vectors. But because I moved in a clockwise direction, we refer to it as a negative angle. So that angle might be 30 degrees, but because we moved clockwise, we're going to call it negative 30. Does that make sense? Okay. And really that negative just tells me a direction. Okay. So as you see in the notes here, okay, option 2, or sorry, situation 2 here, where it says negative angle, you move in a clockwise rotation. It doesn't mean that the angle isn't there. Okay, it just means the negative just means it is a directional type thing. Okay, and that's one of the things that confuses people that we haven't seen before with angles, but just a convention that we've developed, and it fits into all the other trig and algebra that we need to do. So, is that doable? Sure. When we talk about like distance, let's say I want to talk about the distance between two cities. Okay, how can I do that? What kind of units could I use? I want to talk the distance between Lima and Walpole. What would you do? What kind of number would you associate with that? Miles, right? That's what we're comfortable with, right? Okay. But if I was in Canada, what would we use? Kilometers. Kilometers. Okay. Probably not so comfortable with that, right? Okay. We have a degree of comfort, especially in the nation that we live in, with feet, inches, miles, right? Okay. But I can also talk about distance in regards to kilometers, meters, centimeters, that kind of stuff, right? In regards to angle measurement, it's the same way. Okay, so distance we can talk about using the same exact distance using miles or kilometers, right? And the numerical quantities that go with those two things would be different, correct? Okay, but it's still describing the exact same distance, right? Okay, so think about it this way: 1 inch is the same thing as 2.54 centimeters, right? So if I have a segment in front of you that was 1 inch, or if it was 2.54 centimeters, is it still the exact same segment? Yeah, okay? So when I put in front of you an angle that's 180 degrees, that is the exact same angle as an angle that's pi radians. We'll talk about that here in a moment, what that means, okay? But degrees is the unit of measurement that you're comfortable with, right? Okay? It's kind of the mile idea. You guys are comfortable with miles. You're probably most comfortable with degrees, okay? And we know that, you know, an angle measurement is simply the amount of rotation that the terminal side has moved about a vertex. Okay, so that's what we're describing there. But the degree is the unit of measurement for the angle, and we know that in a circle, to get from where I start all the way back to my starting point would be 360 degrees, right? Okay, so if I go back to this idea here, if I go all the way around back to where I started, that'd be 360 degrees of rotation, right? Okay, so that angle would be 360. If I break that up into unit increments, basically we have the definition of a degree, which is 1/360th of a rotation around a circle, right? Does that make sense? Okay, so 1 degree is 1/360th of a degree, or a rotation around a circle, which is, you know, obviously something we've been talking about for a long time. You've probably been talking about that since, I don't know, 5th grade, whatever. Okay, but then we get into radians. You remember in Algebra 2 or geometry that we had to, when we started doing sine, cosine, tangent stuff, I tell you how to operate your calculator and to make sure it's in the right mode. Okay? This is where it's going to become important to be able to flip back and forth. In those courses, in Algebra 2, in Geometry, our mode always had to be degrees. Okay? Because we didn't introduce radians at that stage. Now we have to flip back and forth between which one's which. Okay? You know, if we had to do distances, if our calculators did like unit manipulation with distances, it'd be the idea of if I'm going to do it in miles, I got to change my mode so it's dealing with the English system. Or if it was the questions in kilometers, I had to change the mode so that's dealing with the SI system. Does that make sense? So when the problem talks about degrees and you're using degrees, you're going to use your calculator. You got to make sure your mode's in degrees. Okay? If your calculations are talking about these radian things, you need to take your mode and turn it into radians. Okay? Because it's the unit that is occurring with your angle measurement. Okay? All right. So we understand what a degree is. It's one way of describing an angle measurement. A second way of describing an angle measurement is a radian. Okay? You're less familiar with radians, and they're harder to deal with, but or I guess I don't know if they're harder to deal with, or maybe harder to think about because we don't have a background with them yet. But they are a more natural way of describing an angle, and with the algebra that we're going to do, it's more convenient to do it with radians. Okay, so that's what we're going to kind of do, and then be able to flip-flop back and forth between the two. So you have the urge to always deal with degrees, but you're going to find out that radians is a much more convenient unit. Okay, so what is a radian? Okay, by definition, there it says it's the length of the arc that is inside of an angle, okay, formed by two radii that are 1 unit long. All right, now when we write this, it's not a huge deal that the two radii are 1 unit long. We can change the radius if we want to, and every once in a while. Okay, that phrase right there, might be replaced with the word subtended. Okay? Subtended or intercepted are two words that kind of talk about that arc that is cut off by two radii. Okay? Every time you take a circle and you draw an angle inside that circle, and your rays pass through the circumference of the circle, okay? That circle is divided into two sections then, right? The arc that is on the inside of your angle is referred to as the subtended arc. It's a phrase we use a little bit in geometry, but you might see that a little bit more often now in maybe WebAssigns questions and stuff like that. So that's what subtended means. So if I'm looking at, let's put a circle in this thing. Let's see here. So if that's my angle, my subtended arc would be B to C. Does that make sense? It's the arc that is between those two angles, or so those two rays. All right, so let's talk about what a radian is. We've defined it. Maybe that definition is still a little fuzzy, a little hazy. This is what we are talking about when we deal with radians. All right. So this applet is going to show us creating a circle first. Okay. Pause. There we go. So pretty straightforward, right? We take a segment, okay, and we rotate it about 0, 0, and it traces out our circle, right? Now, to get what we call a radian, we are going to take this radius out, and we're going to line it up over here instead, okay? And then we're going to bend it. Okay, so take the radius, and now we bend it, okay? So what I want you to understand is that when we bent that radius along the curvature of that circle, that red length is still the same distance as it was when it was the radius. Does that make sense? Okay. Now when I do that, we can go from 0, 0 to this other endpoint. We're going to draw a line to that. And now we create an angle, right? that measurement is equal to 1 radian. Okay? Does that make sense? And those of you that are in physics might have heard that's, like 57.29 degrees. You remember hearing something like that? Okay? 1 radian is about 57 degrees. Okay? 57.3 degrees. Might be a conversion factor that you've used in that course. We're going to use a better one. Okay? But that's the idea. Now, if that's 1 radian, what we like to do to get our conversion factor from radians to degrees is start to see how many of those radians we can kind of place inside our circle. So we take that radian, we cut and paste it, and that would be 2 radians, right? So that's about 114 degrees. Okay? And then we could probably fit 1 more radian in up there, right? In the top semicircle. That would be 3 radians. So that green angle, okay, from this being an initial ray right here, and this being my terminal ray, we've got that green angle is 3 radians. This little portion right there is 0.14129, whatever, okay? And that ends up being, when I collectively put that with 3, it actually ends up being perfectly pi radians. Okay? Does that kind of make sense? All right. So, and you can do this with any circle of any radius. If I'm a circle of 5, the radius of 5, I should take that segment of 5 inches or 5 units, whatever it is, inches, miles, feet, whatever you want to use, and I should be able to pluck that out and bend it around the curvature of my circle, and in one semicircle, it should show up pi times. Does that make sense? Okay. In regards to a measurement, a degree, how many degrees would that be? 180, right? So there's our conversion factor. 180 degrees is equivalent to pi radians. Okay? 180 degrees is equivalent to pi radians. So now if I know that, that allows me to take any degree and change it to radian, or any radian and change it to degrees, right? Now, usually what we like to think about is not only that fact, but going all the way around the circle. If that's pi radians, that would be 2 pi radians, right? So 360 degrees is equal to 2 pi radians. Okay? So showing that demonstration one more time. Take a radius, pluck it out, bend it on the curvature. There's 1 radian. Okay? And then you should be able to put that thing in there and throughout your entire circle 2 pi times. So 6.28 times that angle should fit into your circle. Does that make sense? Okay. So what they're going to ask you to do from time to time is, can you convert back and forth between degrees and radians? And this is going to be, so one of the reasons I want to kind of go slow initially is because this is going to be a process that we use almost every day. Okay. You guys are more familiar, more comfortable, like I said, with degrees, but the algebra sets itself up best for radians. Okay. And even in the past, you might get to a problem, and it might be in radians. You might, oh man, I don't know how to do this in radians. I know I struggle with radians, but maybe I can transfer it into degrees and do all the work with degrees, and then at the end transfer it back into radians, because that's how the question is going to be want to be answered. Okay. So it allows us to flip back and forth. So for instance, if I'm trying to find the rate of something, the speed of something, just to get an understanding of whether my answers make sense, maybe I'm trying to find the speed of somebody riding a bike, and I'm doing that in kilometers and minutes, okay? That would be, when I get an answer, and I think about a number that represents kilometers per minute, I don't have a really good visual or understanding of what that is. Does that make sense? But if I take that kilometers per minute and change it to miles per hour, and I can find out that my bike rider was going 5,227 miles per hour, that probably tells me I've done something wrong, right? Okay? But with the minutes per kilometer, or sorry, kilometer per minute, maybe I can't make that argument because I don't have an understanding of that unit very well, or that rate very well. So you might initially not have an understanding real well of radians, but you have a really good understanding of degrees, right? So when we're working with radians, it might be beneficial to every once in a while turn it over to degrees and see what it looks like in degrees, and does it make sense in degrees? If it does make sense to you in degrees, if it's logical, then you're probably correct with your radian measurement. Okay. So what they're going to do is ask you, can you express something in radians if it's provided in degrees? And what I want to do before we even get to dealing with this is kind of just open your eyes to some things that you've done, maybe in another course, maybe you've done it, hopefully you've done this in science a lot for the last 3 or 4 years. But and I know we did it in geometry, but we struggled with it collectively. It's dimensional analysis, it's conversions. Okay, so let's say we have, let's go 38 centimeters. Okay, 38 centimeters, and I want to change that into feet. Okay. So what I always do, and I think this is really beneficial whenever you have to conversion, and we do a lot of them, okay, is you start with obviously the rate or the unit that is providing the problem. Okay, I leave a little bit of space here in the middle, and then I write down over here what is the unit that I want to finish with. Okay, and what that basically sets up for me is a visual that says you need centimeters to disappear, and you need feet to appear. Okay, through the multiplication that we're going to do, that has to happen. Okay, well the only way, and these are always going to be fractions, the only way that I can get centimeters to disappear, because right now it's in the numerator, right, is that I get a label of centimeters in a denominator somewhere, correct? Does that make sense, everybody? So I'm going to put centimeters right there. Okay? Now the reason I went from centimeters to feet, I went from one unit, the SI unit, to the English unit, or English system, is because we need a conversion rate. We need a factor that allows us to transfer from one system to the next. And that factor is that 1 inch is the same thing as 2.54 centimeters. Okay? So that, we're doing a distance idea here, but that's kind of how we would, that's the rate, the conversion rate, that maybe if we were in degrees or radians that we would use. Okay? We need a tool that gets us from one type of measurement or one system to another. Okay? Now, if I'm at that stage, if I think about what's going to happen here, are those going to cancel? So if I just left it that way, my only units left over would be what? Inches, right? Is that the unit that I wanted to show up at the end? No, I wanted feet, right? So because they're different, it tells me keep going with multiplication. Develop another conversion factor. Okay? Well, is there a direct link between inches and feet? Yeah. Where does inches have to go here? Bottom. Feet shows up here, right? And now I can put in the numbers. 1 foot, 12 inches, right? So you take 38 times 1 times 1, and then I take 2.54 times 12, and I get 38 over something pretty close to 36, don't I? Or sorry, not 36, 30. 38 divided by 30 or something like that. And that would tell me how many feet that is. Does that make sense, everybody? And that's how we get rid, that's when we do conversions, that's how we go from one unit to another unit. So, when we deal with the 2 examples that they ask us here with degrees and radians, it's not as difficult because there's only one conversion. Okay? The reason I show that is if you start to scroll through some of the pages here, you're going to find out we're doing some story problems into this section with angular velocity, linear velocity, and how those 2 things relate to one another. And they might talk about, a wheel revolving 15 times per second, and they want you to talk about how fast is that in miles per hour. Okay.
Pardon the interruption. This is just a note that Mr. Root's classes need to report to study hall for the remainder of the day today. Again, Mr. Root's classes will need to report to study hall for the remainder of the day. You will eat B lunch. Also, Jeremiah and Isaiah Bolin, please stop by the office. Thank you.
All right, so if you scroll up to this blue box right here, it tells you there's 2 conversion factors, and they're essentially reciprocals of one another. And it's the fact that they're created because we know that 180 degrees is identical to pi radians. Okay, And if you want to memorize those two things and memorize when to use them, that's fine. I think memorization of those is going to clutter your mind. Understand that 180 is equal to pi. Okay? 180 degrees is equal to pi radians. And that allows you then to always have the right conversion. Okay? If I have degrees, I want to get to radians. Okay? Don't degrees have to be down there so they cancel out? Okay? Is there a direct link between degrees and radians? And there is. We just talked about it. The link was at 180 degrees. 180 degrees is the same thing as pi radians, right? Okay? So I know because I started with degrees as the original initial amount, that degrees had to be in the bottom, had to be in the denominator of my conversion factor. Okay? Because now they're going to cancel out, right? And here's the thing, we now have, and I will do a lot of preliminary canceling here in a moment, but the idea is, that's a fraction times a fraction, right? So do I get 65 over 180? Units cancel out, degrees cancel out, and left with the radians, right? Well, what's 60 divided by 180? Yeah, it's 1/3, right? So you get 1 pi over 3. I'm going to write that as radians. So pi over 3 radians. Okay? So 60 degrees is the exact same thing as pi over 3 radians. Okay? Did anybody know that? Anybody seen that in physics, deal with that in physics at any time? Good. Okay, so it's new information. That's something we'll commit to memory. Okay? And we're going to use, through the things that we do, think back to geometry. Remember special right triangles? 30, 60, 90 triangles? 45, 45, 90 triangles? Okay? We like to use those a lot in trigonometry to explain things and show relationships. Well, a 60-degree angle is going to get used a lot in this course. We don't like to deal with it as a degree. We like to deal with it as a radian. So whenever you see a 30, 60, 90 triangle, there's a pi over 3 radian angle in there. Okay? There's also a pi over 6 radian angle. That's the 30 degrees. Okay? Does that kind of make sense? Okay? And we're going to use these a lot where there's going to be kind of a handful of angles that you memorize. I think there's 17 of them that we will memorize. And I say memorize, but hopefully we use them enough that it just becomes second nature. A couple of them pretty easy. For instance, this would be, that angle right there would be pi radians, right? Which would be 180 degrees, correct? How many degrees is that? 90, right? You took 180 and divided it in half, right? So if I take pi and divide it by half, what do I get? Pi over 2. So 90 degrees, I take 90 degrees, multiply it by that conversion rate. What's 90 over 180? 1/2. So 90 degrees is pi over 2 radians. That's another one that we use 90-degree angles a lot in this course. Okay, so it's better to use pi over 2. It's more convenient or natural eventually to use pi over 2. Is that doable? Okay. And we'll see a lot of that stuff. If you're concerned about, do I need to know tomorrow that pi over 6 is 30 and pi over 3 is 60 and pi over 2 is 90 and 5 pi over 6 is 150? No, you don't need to know that tomorrow. But we're going to kind of develop an understanding of those things pretty quickly, and hopefully eventually they become kind of second nature. You guys ever heard of the unit circle? This is in physics, okay? So the unit circle is basically the tool that allows us to learn those things and use those things, those radian measurements, more efficiently. This one says express pi over 6 radians in degrees. So pi over 6 radians. I want to get to degrees. Okay. So the unit of radians needs to cancel out, right? So I need radians down here on the bottom, and I need degrees to show up on top. So in this case, I'm going to use the reciprocal of the factor that we're using in part A. I'll put 180 on top, and then pi on the bottom. Okay. I always get the question from 2, 3, 4 people every year: how do you know to use 180 over pi or pi over 180. And it's because I know the unit that I start with and the unit I want to get to. Okay? So basically, the unit that I start with, I want that to cancel out. So that means that phi has to go on the bottom in this case. So the radians cancel. Okay? I get now, I'm just going to, usually you probably won't write it as deliberate as this, but we get 180 over 180 pi over 6 pi. What happens to the pi's? Cancel out as a factor of 1. How many times does 6 go into 180? 3. So we got 30 degrees there is the same thing as pi over 6. Okay? And they're going to ask you, okay, we got one over here on the board. Let's do a different. Let's go, what if I said 8 pi over 3 radians, and I want you to change that into degrees? Okay, well, what needs to go on the bottom here? Pi radians. And what needs to go on top? 180 degrees. Okay? So I multiply those together. 8 pi times 180 on top, right? 3 pi on the bottom, right? What happens with your pi's? Cancel out. How many times does this 3 go into that 180? 60. Okay, what's 8 times 6? 48. So 8 times 60 is 480. So 8 pi over 3 radians is the exact same thing as 480 degrees. And we're going to get a lot of angles like that, because that's bigger than 360, right? You're going to get a lot of angles dealing with a lot of angles that are larger than 360 degrees. When we talk about, and I just kind of give you the visuals of how they write stuff in WebAssign and stuff like that, this is considered standard position. Okay, every time we deal with angles, okay, if I want that angle there, I can deal with that angle. Maybe, I wish I could cut and paste it, but I can't. Maybe that angle is the same as that one, okay? And I can deal with it here. Or maybe it's the same as that one, right? So if all three of those angles are congruent, the information that I learn about any one of them is the same for all of them, right? Does that make sense, everybody? So if that's the case, then it makes a whole lot more sense to take this angle here and slide it to here. Slide that vertex to 0, 0, and deal with the angle there. Does that make sense, everybody? And that's called standard position, because it makes the algebra, it makes a lot of the things we would like to do a lot easier if this is the positive x-axis and that is the vertex, and that's called standard position. Okay? You guys remember, you guys talked about vectors in physics, right? Okay? Well, if I have a vector, and this is the concept, if I have that vector in physics, okay, it's kind of a pain in the butt to deal with it at a starting point of 8, 2, right? But you learn in physics that that vector is the same as that one, right? It's the same as that one, right? So algebraically, it makes more sense to allow that vector start at 0, 0. It just makes your calculations a little bit easier. Well, if I think about the rays of an angle, the rays of an angle are essentially vectors, aren't they? Okay, so we like to start in standard position. Now, when they show this little arc here, that little movement, that's showing you that that's the angle we're interested in. Okay, you see this one, they're tracing out a negative angle. This one here, they're tracing out a positive angle, but that positive angle is going to be bigger than what? 360. Okay, the idea is, if I can show it here, they're showing, tracing out basically that point on C. So I've traced out 360 degrees there, but then I go a little bit further. Does that make sense? Okay. Something that's important is this angle here, and come over to this one here. If I overlap them, do they stop at the same spot? Think about the terminal sides there, the two blue sides. Do they stop in the same spot if I overlap them? That stopping at the same spot is referred to as coterminal. Co means together, terminal means end, all right? So they end together, they end at the same location. One of them might be 40 degrees, the one on the bottom might be 40 degrees, the one on top might be 360 plus 40, right? It might be 400, okay? But they are coterminal. So everything, what's nice about that, if I ever want to learn something about a 400-degree angle, it's everything that you know about a 40-degree angle. Does that make sense? So when they give me stuff like that, they tell, hey, work with a 380-degree angle. No, I'm going to work with a 20-degree angle, okay? Because 20 and 380 are coterminal. Does that make sense? And it just makes things a little bit easier to deal with. Same thing with negative angles. If I want to talk about maybe a negative 90-degree angle, it might make more sense to talk about a positive 270-degree angle. Okay? We'll pick up with that stuff tomorrow. There is a 5-1 assignment, web assigned. Not due anytime soon, but you might be able to get a jump start on it. You have a fantastic day. Thank you.
What?